Welcome to the video that we're going to talk about how to identify characteristics of rational functions from graphs. We'll be looking at some important characteristics of rational graphs by using just the graph itself today and making sure that we can write them in the proper notation. So some of the things we're going to be looking for will be vertical asymptotes, horizontal or possibly slant asymptotes, holes in the graph, x and y intercepts, and writing our end behavior and domain. So we'll start off with an easier one. And I'm just going to go through each of the characteristics that you'll see below. First thing I want to find is any vertical asymptotes. And to do so, I'm going to look for any vertical dashed lines and then try to write the equation of that line. So I see that I have one here. It goes through the x coordinate -4. So I know that the equation of that line is just going to be x equals, +4. So when I write my vertical asymptote, I'm going to write it as x equals 4. Horizontal or slant asymptotes, those are going to be found by looking for those horizontal or possibly slanted looking dotted lines, in which case I just see one. I see that it goes through the y value of 1. So in this case, I would write my horizontal asymptote as y equals 1. All right, next up, it says to look for holes and then our intercepts. So a hole in the graph will look just like what you would expect. It will be a hole in the graph. There are none on this one. We'll see one on the next example. X-intercepts. Those are places where our graph crosses the x-axis. So that's what we're looking for, is places on the graph where our curve goes through the x-axis. And I see one right here. It goes through the point -1, 0, and that is how we would write our x-intercept, is at -1, 0. Next up, we're going to look for our y-intercepts. Again, we're going to look for where the curve goes through the y-axis this time. So any place where we see it crossing through the y-axis. Now that's right here, but let me zoom in a little bit here. If you notice, our graph, the coordinate plane, looks like it's counting by halves. So this is -1/2 on the y-axis, which means this point looks like it's approximately -1/4 on the y-axis. So I would write that as a y-intercept, so it looks like this. So I'm going to put that down here underneath y-intercept, the point 0, -1/4. And then the last two things we'll see on our requested information are domain and end behavior. Domain takes into account any vertical asymptotes or holes in the graph, and we're looking at where is the x undefined. What are our inputs that can't be used? And in this particular graph, the only one that can't be used is where x is equal to 4, since we have a vertical asymptote there. So I'm going to come down here and I'm going to write my domain so that I communicate that we cannot use -4 as an input. So I'm going to say we'll start with -infinity and we're going to end with +infinity. In between, we get to 4 and we encounter a problem. So I would say everything from -infinity up to, but not including 4. We use the little u to indicate that we're saying and in mathematics. And then we would say everything from 4 to +infinity. I use the parentheses around 4 to indicate that I'm not including 4 as part of my graph, but everything on the left side of 4 or the right side of 4 is fair game. All right, and then the last thing we're going to look at is the end behavior. Now, end behavior is directly related to either your horizontal or slant asymptote, depending on what you have. So when you write your end behavior, it will be written in this form. It's always going to take the form as x approaches -infinity, y approaches, and then you're going to fill in the blank. And then we say as x approaches +infinity, y approaches, and then you're going to fill in the blank. The key to this, guys, is these two blanks will be the same thing. And even further, those two blanks are going to be directly related to your horizontal asymptote. But let's look at the graph and kind of decide what we've got. So if I trace along that graph from going towards the left, so as my x values are getting smaller as my x's are going towards negative infinity. We can see that our graph is sort of hugging that horizontal asymptote. So as we go to the left, as our x's go towards negative infinity, our y values are approaching 1. So that's why I would write y is approaching 1. And then we can look at the right side of our graph. So as I look at the right side of my graph, as we go towards positive infinity on the x-axis, again, what are my outputs? What are my y values getting close to? In other words, I see that my graph is getting very close to y equals 1. So when I write my end behavior, I'm going to write y equals 1. Or y is approaching 1, not equals 1. It's getting closer to 1. Okay, so that is what it looks like to find those characteristics just by looking at the graph, and that's what we're doing today. We said there are no holes, so I would just write none here. Okay, let's try another one. All right, so new graph. Let me zoom in a little bit so we can get a better idea of what's happening. We're going to go through the same key aspects. So I'm going to start by looking for any of those vertical asymptotes, so any places where the vertical line is dashed. I've got 2 this time, and those 2 are at where x is equal to -2 and x is equal to 3. So my 2 vertical asymptotes are going to be when x is equal to -2, comma, and x is equal to 3. Those are writing the equation for my vertical asymptotes. Okay, next up, horizontal or slant asymptotes. So now I look for places where I have a dashed or slanted dotted line. In this case, it's dashed again. So I'm going to write the equation of that by just writing what the y value is. We go through -2. So my horizontal or slant asymptote is y equals -2. Okay, next up, we're going to look for any holes in the graph and intercepts. So now when you look at this graph, you can see right in the center of the graph, there's an open circle. That open circle denotes that there is a hole in the graph. And what that means is that everything to the left of the hole and everything to the right of the hole exists. But when you get to that specific ordered pair, there is no value for that function. So we're going to look at how do we write that as a characteristic of the graph. Since it's representing a point that doesn't exist on the graph, I'm going to write any holes in the form of an ordered pair. So I can say that that hole looks like it exists at the point 0, 0. That's what I'm going to write for the hole in the graph. Next up, let's talk about x-intercepts. So when I'm looking for my intercepts, I'm looking for where does it cross the x-axis. Well, here's one place where it crosses the x-axis. And then some of you might think, well, there's another place at 0, 0. Well, for sure I agree that 2, 0 is an x-intercept. But in order for it to be an x-intercept, it has to actually cross through the x-axis. The hole does not actually have a value on the x-axis. So if you write something down and it's a hole in the function, it cannot also be an x-intercept. So we do not write that as an x-intercept. Let's take a look at our y-intercepts. The only y-intercept that's possible, again, is right there where the hole is. If a hole can't also be an x-intercept, it cannot also be a y-intercept. So in this case, there is none. All right, next up, we're going to write our domain. So we're looking at what is the domain from left to right on this function. It is directly related to 2 things. It's directly related to what we wrote in for our vertical asymptotes, so the x values at our vertical asymptotes. And then it's also directly related to the x value of the hole in the function. And the reason for that is because your x value, your input, does not exist. So we're trying to identify all the places where we do not have elements that are actually in our domain. So this one's going to have a few parts to it. And here's another way you can think about it. Start from the left of your function. Okay, so I'm starting here on the left, and I trace along the function, and as soon as I come along a place where I'd have to pick my pencil up to continue to draw on the function, that's going to be a break in my domain. So because I'm good until I get to -2, my first break in my domain is at -2. Now, I'm going to pick up on the other side of -2, so I'm going to use that to start off the next part of my domain. And then again, if we trace along here, let me move this down a little bit, trace along from -2, we're good until we get to here. And then we'd have to pick up our pen again. So that's at the x value of 0. So our next x value that's an issue happens at 0. So then we say, okay, we're going to pick up on the other side of 0. So let me take my pen again and put it on the other side of 0. Oops, sorry about that. And trace again until we run into another issue. And this is where we'd have to pick up our pen again because our graph skips over the place where x is equal to 3. So that's another problem area in my domain. That's going to be the next break in my domain from 0 to 3. And then we can pick up and go on the other side of x equals 3, and we keep going forever. We never have to pick up our pencil again. So at that point, we would say it's from 3 to infinity. So this time we have 4 parts to our domain. All right, end behavior. Last but not least, end behavior is directly related to what you wrote for your asymptote or your horizontal or slant asymptote. So just like I said before, we're going to write the same thing every time to start. It's always going to be this kind of template that we're using. The only thing we have to change each time is what y is approaching. Now you can look at the graph and figure this out. So what I suggest is we take our a pen or something and we think about what's happening as we go to the left of our graph. So as the x's are getting smaller, as the x's are going towards negative infinity, again, it looks like our y values are staying really close to that horizontal asymptote at y equals -2. So y is approaching -2. And then we can do the same thing on the other side of the graph as we go towards the right of our graph, as our x's get larger. Now, some of you might be disturbed by the fact that it looks like our function crosses over an asymptote. We're going to look at why that can happen in a little more detail later, but for now, understand that vertical asymptotes are like brick walls. You cannot go through a vertical asymptote. But think of horizontal asymptotes as being like a floor where you have stairs that you can go up and down to pass through the floor. The big idea here is that our function may pass through a horizontal or slant asymptote, but it's going to always stay really close to that asymptote. So what I've got happening here is my function passing through the horizontal asymptote, but hugging that horizontal asymptote. So it's still, as we pull away from the origin and go to the right, we still have our function staying close to -2 as an output. Okay, I want to talk about one thing on this slide, and then the rest of it is just like what we've done. The only thing that's different on this one is the idea that we have this slant asymptote. And we see it's a slant asymptote because it's a slanted dashed line. And you can also sort of see how the function behaves around that slant asymptote. As you go out away from the origin, it stays really close to that slant asymptote. How do you write the equation for that slant asymptote? Because that's what this is asking. So let's look at this. In order to write the equation of any line, if you know 2 things, you can write the equation. So let's think about back to algebra 1. Y equals mx plus b. If we know the slope of the line and we know the y-intercept of the line, we can write an equation. So when I'm looking at this, I'm going to identify where I think the y-intercept is and then try to figure out the slope. Now, this is, maybe not exact, but we can sort of estimate. Again, this is counting by halves. It's a little bit more than a half, closer to a half. I'm going to estimate that my y-intercept is 2/3. Now, this is just a complete estimation. It does not have to be exact. I'm sort of guessing here. To find the slope, you can do a slope triangle. I'm actually going to identify 2 nice points. In other words, 2 places where I cross through what I call a lattice point. So there's one, and maybe here's one. Now, you should watch your scale. Our y-axis and our x-axis are counting by the same things, so it's okay to do it this way. If they weren't, you'd have to be a little more careful. But it looks like we're going to go up 1, right 3 to get our slope. Up 1, right 3. It's a positive slope. And then all we have to do is put all of that together. Y equals 1/3 is our slope, x, and it's a -2/3 because it's, I guess I should have written that up here. It's on the negative part of our y-axis. This is your slant asymptote. Everything else you do remains the same. In fact, your end behavior is also directly related to that slant asymptote. So to write your end behavior, just like we did on the previous ones, we started the same way. Same template. We just have to fill in the blank. And the blank is exactly what we wrote here. It's what our slant asymptote is. So I'm just going to write 1/3 x minus 2/3, 1/3 x minus 2/3, because our function, as we move far away from the origin, as we look at the end of the graph, in either direction, it's staying really close to that asymptote. All right, that's a quick overview of how to pull out the information on a rational graph from the graph itself. We'll talk more about how to do this algebraically in class.